Logical equivalences involving quantifiers. That means in propositional logic, with the same fundamental concept behind the logical equivalences, we'll see the logical equivalences. Here, we'll use the predicates and quantifiers. That's the same thing. Okay. The concept is same. Statements involving predicates and quantifiers are logically equivalent if and only if. Then tell me, when two statements are said to be logically equivalent, what is their condition? Any two propositional statement or mathematical statement are said to be logically equivalent. What is their condition?
When the truth tables are equal.
Yeah, truth tables are, that means when both have same truth value, truth tables are equal, truth columns are equal. That means if and only if they have the same truth value. Yes. No matter what, or okay, you can write a which. No matter which predicates are substituted, which predicates are used or substituted, and which domain is used, domain of discourse, or only simply domain. That means whatever the domain and whatever the predicates and quantifiers, if both these statements or both these mathematical statements or logical expressions have the same truth value, then we can say that they are logically equivalent. Notation, same notation we'll use. That means same notation means two statements. Let one is S, another is T, involving predicates and quantifiers. Are logically equivalent. That's the same notation. That is, S is a logical expression and that is equivalent to T. T is a logical expression that two statements S and T both are involving predicates and quantifier. So we can write S is equivalent to T. That is the notation. Okay. So that for all x, P of x and Q of x, that is equivalent to for all x P of x and for all x Q of x. the same domain is used. For the proof. That means we are going to show that these two mathematical expression or logical expressions are equivalent to each other. That means we have to use the common domain of discourse. Whatever the your predicates are P and Q. That means suppose we have particular predicates. Predicates are P and Q with a common domain. That means domain D, that is for P and Q, that is same domain. Domain of discourse D. That means domain for predicate P, that is also D, and domain for Q also D. Then we have to show that both these logical expression have the same truth value. Okay. Then how to prove? We can take this implies this and this implies this. That means LHS implies RHS and RHS implies RHS. The converse part. Okay, we'll see the proof. First, we consider the first part. Let for all x, P of x and Q of x, this is true. And we are taking this is true, and we are taking a element A in the arbitrary element in the domain D. Then what will be true? For all x, P of x and Q of x is true. That means what? Which is true? A is any element in the domain. For all x, P of x is true. That means for that particular element, it will be true. That means P of A conjunction Q of A is true. Okay. P of A and Q of A is true. That means that is a simple. That is P of A is true and Q of A is true. Here, what is A? A is any arbitrary element in the domain. So, here A is any arbitrary element. Taken from the domain D. So, P of A is true. That means A is any arbitrary element. So, P of A is true for all elements A. That means you can write P of X is true. For all X. Similarly, Q of A is true when A is any arbitrary element from the domain. That is the same thing. P of that is the same thing. Q of X is true for all X. P of X is true for all X. That means what? Predicate P of X is true for all X. For all X means you can write for all X, P of X is true. Like the same way, q of x is true for all x. So you can use for all x, q of x is true. So for all x, px is true, and for all x, qx is true. That is the same thing for all x, p of x, and for all x, q of x is true. That means we have taken for all x, p of x and q of x is true, and implies that for all x, px and for all x, qx is true. That means we proved that for all x, p of x and q of x implies for all x, p of x and for all x, q of x. That is the first part. And conversely, you can prove that, take this right side and prove that for all x, px and qx. Okay. Conversely, first we'll take the right hand side. That means for all x, p of x and for all x, q of x is true. And let an arbitrary element A in the domain D. The same thing just implies for all x, px and for all x, qx is true. That is the same meaning for all x, px is true, and that is the definition of a conjunction. For all x, q of x is true. Then for all x, px is true, and for all x, qx is true. So since we get that A is any element in the domain D, for all x it is true. So for A is a element, so P of A will be true. That means for all x, P of x is true. Since A is the element in the domain, as it is all x it is true, so A is any element, so P of A will be must be true. That means since A is an element in the domain D, implies here for all x, P of x is true. A is an element in the domain, so P of A will be true. P of A is true. Similarly, Q of A is also true. So P of A is true and Q of A is true, implies P of A conjunction Q of A is true. Now see, A is what? A is any arbitrary element in the domain D. So here since A is taken, A taken an arbitrary element from the domain D. So P of A and Q of A is true. So that will be true for any element A, for all element A. That means P of X conjunction Q of X is true for all X. So for all X, this is true. That means for all X, P of X and Q of X is true. That is, we have proved that for all x, p of x, and for all x, q of x. We have taken this, we got that this implies for all x, p of x and q of x. So we conclude that this equivalent to this. That means p equivalent to q. P implies q and q implies p. That is the same thing, p equivalent to q. So this concludes that for all x, p of x and q of x, that is equivalent to for all x px and for all x qx. Any doubts in this proof? Any doubts in this proof? Okay. Then we will see negation of quantifiers. Negation of quantifiers. So there are two quantifiers. One is universal quantifier and another is there exists quantifier. So first one is negation of for all x, p of x. What will be this? This will be equivalent to negation of for all x, px. That will be there exists x, negation of p of x. Another one is negation of there exists x, p of x. P of x is any predicate. So this will be equivalent to. So negation of for all, that is there exists x, negation of px. So negation of there exists x, p of x, that will be for there exists. So that will be for all x, negation of p of x. These two laws or two equivalences are called De Morgan's laws for quantifiers. That means negation for two quantification. One is universal quantification, another is existential quantification. So negation of universal, that is existential x, and negation of existential, that will be universal. Okay. We'll see the proof. Okay. First, we'll take negation of for all x, p of x is true. Then we are going to the proof of first one. First one is negation of for all x, px, that will be there exists x, negation of px. Then what will be? This is equivalent to what? Negation of for all x, px is true. Then what will be false? We know that if the proposition is true, then negation of that will be opposite to that. If the negation of this is true, then what will be false?
For all x, p of x is false.
Yeah, that means for all x, p of x will be false. Okay, that means see, for all x, px is false. That means what? For all x, px, that is false. What is the concept behind it? That means there exists a counterexample. That means there is an element X in the domain for which the given predicate P of X is false. It is true for all the elements X is predictably true. As it is false, you must have an element present in the domain for that given predicate is false. That is the when universal quantification is false. That is the definition. When universal quantification is false, if you are getting at least one element in the domain, for that element universal predicate P of X will be false. Then the universal quantification is false. Okay. That is same as I am writing the same statement. There is an element X in the domain for which P of X is false. Then what will be true? P of X,
Negation.
yeah, negation of P of X is true. See, this statement is equivalent to what? There is an element X in the, forget about all these things. There is an element X in the domain for which this is true. So this is true. There is an element X in the domain such that this is true. That means there exists X. Negation of P of X is true. That is the definition of there exists. That means we have taken that negation of for all X Px, that is equivalent to this. This concludes that negation of for all X P of X, that is equivalent there exists X, negation of Px, not simply Px. So negation of for all X P of X, that will be there exists X, negation of Px. Same, the proof of second, you can prove it. Proof of second, that is negation of there exists X P of X, that will be equivalent to for all X, negation of Px. Okay. I'm showing one part. When the domain has finite number of elements, let n elements x1, x2, x3 like this xn. Then negation of for all x px, what will be this? This will be equivalent to, any idea? When the domain has n number of elements, x1 to xn, so negation of for all x px, we are going to see this. So that will be negation of, what is for all x px? What is the universal quantification for finite number of elements? That is P of x1 conjunction P of x2 conjunction up to P of xn for universal quantification. Okay. We know that negation of P and Q, that is negation P, disjunction negation Q. That is also De Morgan's law one of the C. Negation P and Q and R like this. So that will be equivalent to negation of P of x1 disjunction negation of P of x2 disjunction like this, disjunction negation of P xn. Let us see negation of this. So this one disjunction, this one up to this one. So that is same as disjunction means that is existential quantification. There exists disjunction of what? Negation of Px. Okay. That is also one type of proof, negation of for all x Px, that is equivalent to there exists negation of Px. What is the negation of the statement is given? There is an honest politician. What will be the negation of this? Also find the negation of the statements. English statement is given, there is an honest politician. What will be the negation of this statement? Okay, first we'll make in the form of predicate. Let P of x denotes the predicate x is honest. X is honest. That is the predicate we have chosen, x is honest. Then the given statement is there is an honest politician. Express the given English statement in the form of predicate or quantification. You will see that is what is the negation of this. Question is using predicates and quantifier. Don't write directly the statement. You have to use the predicate and quantifier. So there is an honest politician. So from this we are letting a predicate, that is x is honest. The given statement, that is there is an honest politician. Is represented by. Then tell me, just represent this sentence, there is an honest politician, using predicate and quantifier. What will be this? P of x, we have taken x is honest. Then what will be the mathematical expression using predicates and quantifier? X is honest. That there is an honest politician. What will be this? There is means that is existential quantification. There exists x. P of x means x is honest. P of x. See, when the predicate is x is honest, we have written there exists an honest politician. That is the same as there exists x P of x. Where what is the domain? Then what is the domain here? Any idea about domain?
All politicians.
Yeah, all politicians. Domain consists of all politicians. From all the politicians, we are taking x is honest. So The given statement, we have represent the given English sentence using the predicate and quantifier. We have taken the predicate P of X, that is X is honest. And the given sentence, there is an honest politician, that is expressed as, that is there exists X, P of X. So we are going to find the negation of there exists an honest politician. That is the same thing, negation of there exists X, P of X. The negation of there exists X, P of X is, that is the same thing, negation of there exists X, P of X. Which is equivalent to what? We are going to find negation of this English sentence. We have first expressed the English sentence in terms of mathematical expression, that is there exists X, P of X. So we are going to find the negation of English sentence, that is the same thing, negation of there exists X, P of X. Then what is negation of there exists X, P of X?
For all X,
For all
negation.
X, negation of P of X.
Yeah. For all X, negation of P of X. So we have taken what is P of X. We know P of X is honest. So we have to find negation of P of X. We have to write for all X. There is, that is there exists, that is existential quantifier. The negation of there exists, that will be for all. So for all means for every. So P of X is honest. So what will be negation of P of X?
X is not honest.
Yeah, X is not honest. That means C, negation of P of X, that will be X is not honest or X is dishonest. Then the negation answer is for all X, negation of P of X. That English sentence will be what? For all X, negation of P of X. See, there is an honest politician, that is there exists X, P of X. Negation is for all X, negation of P of X. So for all X means for all or every politician is dishonest. You can write this in English sentence, every politician is not honest. That is the answer. That means for all X, X is what? X is any politician, for all politician. That means you can write every politician, negation of P of X. P of X is honest, so X is dishonest, that is negation of P of X. So the English sentence is every politician is dishonest. That means sentence was there is an honest politician. The negation of the sentence is every politician is dishonest, using De Morgan's law, using also predicates and quantifier. Okay. And the negation of all Americans eat cheeseburger. That means sentence is given, all Americans eat cheeseburger. What is the negation of this? Question is using predicates and quantifier. So you can write all Americans eat cheeseburger. You can write all Americans do not eat cheeseburger. Cheeseburger. That is the simple negation. But using predicate and quantifiers, how to find the negation. Only remember, we have to write a predicate first. Then tell me what will be the any predicate. Predicate means that contains a variable. That is important. You can take any variable x, y, z, whatever the variable you have to take include a variable. All Americans eat cheeseburgers. Then tell what will the predicate here first.
Eat cheeseburger.
You will take a variable x or y or z, whatever the variable. Let c of x. We have taken c of x. That is the predicate. X eats cheeseburger. That is the predicate we have taken. Now we will convert the given English sentence using our taken predicate. The given statement, that is all Americans eat cheeseburger. Is represented by what? All
For all x, p of x.
Yeah, you can write for all x. Here we have not written p of x, we have written c of x. You can write pq, whatever the symbol. C of x. That means we have converted the given English sentence by using the predicate and quantifier. That is for all x, c of x. That is the conversion of English sentence to mathematical expression of statement using predicates and quantifier. Then what will the domain here?
All Americans.
Yeah, all Americans. Here the domain consists of all Americans. Now we will find the negation of given English sentence. So as we have converted the given English sentence to mathematical expression, that is for all x, cx. So that is we are going to find the negation of for all x, cx. The negation of for all x, c of x is what? That is negation of for all x, c of x. What is that? That is equivalent to what?
There exists x negation of c of x.
There exists x negation of c of x. So we have written c of x, x eats cheeseburger. Then what will be negation of c of x? X does not eat cheeseburger. That is negation of c of x. That means just write this. There exists x negation of c of x in terms of English sentence. We are using this by using all our De Morgan's law. And this negation can be expressed as English sentence. What will be this? There exists x. X means any Americans. So there exists x negation of c of x. That means you can write there is an American. There is an American there is an American who does not eat cheeseburger. Who does not eat cheeseburgers. That is the sentence. Sentence was all Americans eat cheeseburger. Negation of this sentence, that will be there exists a person or American who does not eat cheeseburger. Otherwise, you can also use same sentence. What will be other sentence? Any more idea? There exists X, negation of C of X. Instead of there exists, there is. You can use also some other expressions. What are these? There it means at least one, maybe more. So you can write also some Americans does not eat cheeseburger. That is the same meaning. So we have used there exists. There instead of there exists, you can use for some. So for all, that is universal. For every, for each, like this. Instead of there exists, we can use there is. Also for some, there for at least one, like this. What English expressions? So there is an American who does not eat cheeseburger. That is the same meaning to some Americans does not eat cheeseburger. Express the statement that is given. Every student in this class has studied calculus. Using predicates and quantifier. That means the given sentence is every student in this class has studied calculus. We have to express this sentence only in terms of predicates and quantifier. So first we have to introduce a variable x. So then tell me, using the predicate, then what will be the sentence? Using a variable x. Every student means that will be universal quantification.
So let P of X such that X has studied calculus.
Okay. Let P of X, that will be, see, every student in this class has studied calculus. That means you can write P of X, that is for every student X in this class. For every student X in this class, X has studied calculus. That means see, every student in this class, those who are present in the class or in this has studied calculus. That means for every student X, we have put in student X in this class. X has studied calculus. Here we have taken here the domain of discourse or only domain. What is the domain here? Every student X in this class. Then what will be the domain here? You have to choose the domain.
Every student.
Domain not is every student means all the students. That means that is the set of all students. Set of all students in this class. From set of all the students in this class, we have taken one student, that is X particular. So that is the given statement for every student in this class has studied calculus. That is the same thing for every student X in this class. X has studied calculus. That is P of X. So if we consider the predicate, X has studied calculus. That is the same thing. Every student in this class has studied calculus. For every student X in this class, X has studied calculus. That is the same thing. You don't need to write for every student X in this class. X has studied calculus. You can write let C of X. That is the more clarification. That is X has studied calculus. Then the given statement can be written as, what will be the mathematical expression? Every student in this class has studied calculus. We have taken C of X, that is X has studied calculus. That will be for every student, that means for all. So for all X, C of X. So X, we have taken the domain. Domain is set of all students in this class for all X. That means for every student X present in the class, C of X. That means X has studied calculus. So that is the correct form for all X, C of X, where C of X is X has student calculus, studied calculus, and the domain is important. Domain is set of all students in this class. If you are changing the domain, then that expression will be different. That means, see, if in the same case, the same problem, if we change the domain, if we change the given domain, the domain of this course to then just see any other possible of domain here. One domain is set of all students in this class. Any other domain? Okay. See, other domain, we don't know what are the students. So you can take all the peoples. That is the universal domain. Universal domain you can take. Instead of taking the domain set of all the students in this class, if you are taking the domain, it consists of all the people. Then whatever the given for every person, we have written for every student X in the class has, then X has studied calculus. We have to change that expression. That means express our given statement H. What will the statement? That will be not every student, that will be for every person X. Every person X. If the person is in the student, person is present in the class, then that person has studied calculus. That means if the person X is a student in this class, then that person X has studied calculus. That means we have changed the domain. Instead of taking the set of all the students in this class, if we are taking the domain is set of all the peoples, then every student in this class has studied calculus. That is the same thing for every person X. If that person is a student in this class, then we can say that that person has studied calculus. That means in this case, we have to use two predicates. One predicate is C of X, that is X has studied calculus. We have to choose another predicate, let S of X be the statement. What is the statement? That is the person X in this class. Then the given statement can be expressed as, see, what is the sentence? For every person X, that means for all X. X is from the all the people. See, for every person X from the all the people, if the person X is a student in this class, we have taken if the person X in this class, that means if S of X, then X is a produce. That means then C of X. You can also use this when changing the domain. That is the same equivalent statement for all X, C of X. That is the same meaning for all X. If S of X, then C of X. But domain are different. In the first case, we have taken the domain set of all the students in this class. So H, it already contain the domain all the students only. So only write for all X, C of X. That is for all X, C of X. That means that for every students in this class, all have studied calculus. The same meaning, if the domain is a set of all the people, then we have to use two predicates. One predicate is the person X in this class, where C of X, we have already taken C of X, that is X has studied calculus. That means if the person or people X is a student in this class, then that person has studied calculus. You can use for all this conditional statement. Okay. Express the statement some students in this class has visited Mexico. Using predicates and quantifiers. Okay. Also, one more question. So that negation of for all X, P of X, conditional Q of X is equivalent to there exists X, P of X, and negation q of x. That means these and these are equivalent. Okay, we'll start here. See, some students in this class has visited Mexico. You can take the domain as all the students in this class. So in that case, there exists x has visited Mexico. If you are taking Mexico as the p of x, that will be there exists x p of x, where p of x is x has visited Mexico. If you are taking the other part, that means all the peoples, then you have to introduce two predicates. One is s of x, one is p of x. That is your, that will be not conditional, that will be conjunction. Okay, we'll stop here. Okay, just wait. I'm sending the attendance. This one.